That's up next. In this segment, I'm going to show you how to support activation for a Windows runtime component. If you watched my COM courses, you should be familiar with the mechanics of linking and loading DLLs, and in part 2 of how that gets generalized for COM activation through the standardized DLL getClassObject function that an activatable COM server exports. Well, that supported activation given a class ID. But the Windows runtime doesn't rely on class IDs, so we'll need a new exported function, but it's the same mechanics. Let's open up the module definition file. Here I'll remove the unnecessary library keyword and focus on exports. And I'll tell the linker I want to export the DLL getActivationFactory function. Now there's no magic here. We could naturally export the DLL getClassObject function as well and provide support for classic COM activation even on the same COM classes. But that's not required, so to stress that this is not classic COM and does not rely on classic COM activation, I'll leave that out here. We will want to support DLL can unload now, however. This works the way it always has. If you're not sure, check out my COM courses for a detailed explanation and demonstration. Right, now we need to implement those two suckers. DLL can unload now is fairly straightforward. We just need to provide the ability for the client to control unloading. We need to be able to track how many hens are running around the yard, so to speak. I can then increment this lock in my hens constructor. And drop it back down in my hens destructor. Then my implementation of DLL can unload now can simply check whether this lock is 0. And it returns either SOK or SFalse. Now how about DLL getActivationFactory? It takes a Windows runtime string handle as input. We covered those in the previous module, and it returns an ActivationFactory interface pointer. The class ID is the stringified version of the class name, including the component namespace we found in the middle-generated C++ header file. That's essentially how the caller requests a particular class for activation in lieu of a GUID-based class ID. The ActivationFactory interface is defined in its own header. Normally, I'd also implement DLL main to disable thread library calls. I explain the rationale for that in my COM courses, but let's move on. It's time we implement an ActivationFactory for the hen class, and that's up next. In this segment, I'm going to show you how to write an ActivationFactory for a Windows runtime class. There's the DLL getActivationFactory exported function. We're going to need to new up an implementation of this iActivationFactory interface to return to the caller. Let's create one for the hen class. Again, we're relying on the implements class template to do most of the work here. I'll make sure to enlist the hen factory in the component's unloading count. And the destructor. The iActivationFactory interface adds only a single new method of its own to the mix, and that's what we'll implement here ourselves. Not surprisingly, it's called ActivateInstance. Activate instance is called by a consumer attempting to default construct a particular Windows runtime class. Yes, Windows runtime classes may support additional constructors. I'll show you how later in this module. But for now, this is essentially the gateway for the default constructor. Unfortunately, this function is defined to return an inspectable interface pointer. While all classes must support this interface, it does mean that practically every client will immediately follow activate instance with the call to query interface. It really should have been declared in much the same way as classic COM's create instance method. Anyway, it's too late for that. Here I'm careful to new up a hen while avoiding the standard bad alloc exception. If you're struggling to resolve no throw, it's in the new header. I can then just return whether this succeeded or not. So even though I think it was a mistake to define activate instance this way, it sure doesn't make it simple to implement. I also believe that the Windows runtime was designed for C# and managed code first, and the CLR loves query interface, so it wouldn't have made much difference in that environment, where QI is called repeatedly anyway. Next up, I need to wire up the DLL getActivationFactory exported function to create one of these hen factories. There it is. Now there's no GWIDs to compare, but I do need to compare this Windows runtime string's raw buffer with my hen's class name, so I'll again defer to the Windows runtime string functions. And back down again. Now I can simply compare the requested string with that of my hen's class name, generated by the middle compiler. If they match, I'll new up a hen factory. And if that succeeds, the caller gets an activation factory for the hen class. Otherwise, I'll reject the request, informing the caller the requested class is not available. Now, there are naturally other ways of implementing DLL getActivationFactory, particularly due to the heightened responsibility of class factories in the Windows runtime. It's common to cache these, particularly if the class provides a number of high-traffic static members. But that's an optimization that complicates lifetime tracking, so let's leave it here for now. I think we're done here. Let's see how well this works using both standard C++ and C# as clients. And that's up next. In this segment, I'm going to show you what the client side of the activatable class looks like, and in particular, what it looks like from standard C++ using only the Windows API. So there's really no language projection going on here. This is just the raw ABI programming interface, much like classic COM with a few new constraints. Now the trick is that activation of non-operating system components only works in the context of an app package. And for the moment at least, that means that non-OS components can only be used in Windows Store apps. Of course, what I'm describing is exactly the same as how operating system components are written and activated, so let's start there. Here's a simple console app. This is not a store app, there's no app package. Operating system components may be activated outside of app packages, so this is pretty simple. I need to initialize the thread for use by the Windows runtime, much like what you would do with co-initialize-ex to support classic COM activation. In fact, the last time I checked, row initialize simply calls co-initialize-ex and then returns. But this is considered a bit of future-proofing should the Windows runtime require some additional per-thread initialization in the future. It's unlikely, but you never know. Row initialize is provided courtesy of the row API header file, so I'll quickly include that here. and I'll use WRL's COM pointer for convenience. And we're going to need some Windows Runtime string support, so I'll just include the wrappers and helper functions we explored in the previous module. Of course, we need to tell the linker how to resolve all those API calls, row initialize, and the string functions. Now what type shall we activate? Well, a simple example to use from a console app is the Windows Globalization Calendar class. And I'll just make the names from this namespace conveniently visible. Right, now I'd like to activate the calendar class. To do so, I need its class ID as a Windows Runtime string. I'll only need it as an input parameter, so a string reference will do. And I can use the string provided by the Windows Globalization header. This is just windows.globalization.calendar. If I hit F12, you can see this for yourself. Of course, I can simply copy this name and place it in here. It makes no difference to the compiler. Now I can call the row activate instance function to default construct the calendar class. But like the iActivation factory interface we looked at in the previous segment, it returns an iInspectable interface pointer rather than allow the caller to query for a specific interface directly. At any rate, now I can make the call. At this point, I have a calendar object, but I need to query for its default interface. And I'll just use WRL's as method, since it hides the query interface method for no good reason. Great, now I finally have a calendar interface I can do something useful with. Let's print out the month and year. First, the year using the year property. And then I'll get the full name of the month as a string, with the month as full string method. Okay, let's take a look. First, we initialize the thread for the Windows runtime. Then I create the string reference, an efficient fast-pass string initialized with a calendar class ID. The CTP debugger I'm using is a little wonky, but let's ignore that for the moment. Row activate instance returns the newly constructed object's iInspectable interface pointer, which I then query for the iCalendar interface. I get the year. In the locals window, you can see that it's 2014 as I record this segment, and that it's the month of August. Great! In the next segment, I'll show you how to generalize this code even further, as it's mostly just boilerplate code, desperately in need of a function template to wrap it up. We'll also go the other way and find out what's really going on under the hood. In this segment, let's explore what's really going on here. What's the row activate instance function really doing? But first, let's move all of the boilerplate code into a reusable little helper function. The act of default constructing some class, often called activation, is a very common procedure for Windows runtime apps. What we need is a function that will streamline these steps, creating a string reference, calling row activate instance, and then querying for a specific, usually default class interface. Something like this.